Hello and welcome. Myself, Mr. S.S. Mani, Head of the Department Mechanical Engineering, Chartered Institute of Technology, Polytechnic Etah. I welcome you in the lecture series of course Elements of Machine Design. Today we are in the lecture number 7. Up to this point we have undergone the introduction to the syllabus, what is the importance of this subject in the curriculum of diploma engineering, what is meant by the machine design. We have also studied the concept of stress. We have also undergone the concept of strain. We have studied different types of the stresses, different types of the strains. In last lecture, we undergone through the concept of stress and strain curve, how this curve is drawn by conducting a simple tensile test on a universal testing machine. Now in this lecture we will study the principal stresses and principal planes, what is meant by the factor of safety, and different properties of the materials. So once again I welcome you. So go through the different types of the principal stresses and principal planes. Now consider the element which is subjected to the biaxial stress system, that is direct stress in two mutually perpendicular planes accompanied by a simple shear stress. Now this is the biaxial stress system. This is the plane on which two direct stresses acts. This is the one direct stress, that is the sigma 1. This is another direct stress, that is the sigma 2, and a tau. This is the shear stress which is acting on the element. Then the normal and shear stresses are obtained as shown in the diagram. Now this is the direct stress in two mutually perpendicular planes accompanied by a simple shear stress. In this case, a direct stress in one plane, there is only one direct stress, that is the sigma 1, which is acting on the perpendicular plane, which is accompanied by a shear stress. This is the value of the shear stress, tau 1, and this shear stress acts at an angle of theta degree. Now consider a rectangular body ABCD. This is the rectangular body ABCD of uniform cross-sectional area and unit thickness. Now this body is subjected to normal stresses sigma 1 and sigma 2. These are the two normal stresses, sigma 1 and sigma 2. In addition to these normal stresses, a shear stress also acts. It is the tau. This is the shear stress which acts the plane which is perpendicular to this normal plane at an angle of theta degree. This is the shear stress, simple shear stress. Now in this case, the normal stress across any oblique section, now this is the oblique section EF, this is the oblique section EF, inclined at an angle theta with the direction of sigma 2. This is the direction of sigma 2. This is the normal stress, any normal stress, so sigma t, which is inclined at angle theta with the direction of sigma 2. Now if you understand the simple concept of principal stress in principal planes, then we can say the direct stress along the principal plane is known as the principal stress. Principal stress, principal means major stresses, that is known as the principal stress. in the perpendicular planes which have no shear stress is known as the principal plane. If we take the example of this diagram, consider this rectangular section ABCD. On this rectangular section, the normal stress, that is the direct stress sigma 1, acts on perpendicular plane, and tau, which is acting to the perpendicular to the normal stress at 90 degree. Then according to the definition, the perpendicular plane which have no shear stress is known as the principal plane. If any perpendicular plane which is do not having any kind of shear stress, then that plane is known as the principal plane. That means on principal plane only normal stresses act. And then what is meant by principal stress? The direct stress or normal stress which is acting on the principal plane is known as the principal stress. Once again, try to understand the concept of principal stress and principal plane. When we take or consider a simple object as shown in diagram, in this case there are two normal stresses, sigma 1 and sigma 1, which is acting on this perpendicular plane. In this case, two normal stresses are acting, direct stresses sigma 1 and sigma 2. According to definition, if any plane, say A, B, C, D, or say E, F or AC, on which there is no shear stress is acting, no shear stress, then it is known as the principal plane. And if on principal plane any direct stress is acting, then that direct stress is known as the principal stress. This is the concept of the principal stress and principal plane. Then, according to this concept, sigma T1 means any normal stress, maximum normal stress or principal stress, sigma T1 is given as sigma 1 plus sigma 2. Now, try to understand, sigma 1 and sigma 2 are the direct stresses which are acting on two planes. And tau is the shear stress which is acting perpendicular to this plane. Then in this case, maximum principal stress, value of maximum principal stress is given as sigma T1 is equal to, and minimum principal stress value is given as the sigma T2. The only difference is this plus and minus. When we are calculating maximum principal stress, then we are using plus sign, and we are calculating minimum principal stress, then we are considering minus. Now these are the two principal stresses, keep in mind. Now these stresses are acting on the principal planes only. As we have discussed, there is a shear stress also, which acts perpendicular to these two direct stresses, sigma 1 and sigma 2. Then in this case, the maximum value of shear stress which is acting on this element is given by this formula. This is the formula how we can calculate the value of maximum shear stress which is acting on the element, that is the 1 by 2 sigma 1 minus sigma 2. Now sigma 1 and sigma 2 again are the two direct stresses, and tau is the shear stress which is acting on the plane. Now this is the value of the maximum shear stress. Now why it is necessary to determine the values of principal stresses, that is the maximum principal stress or minimum principal stress, when the elements like crankshaft are subjected simultaneously to torsion and bending. Take the simple example of the crankshaft, or you can take the example of a propeller shaft. When these kind of the elements, when are subjected to the application, in the application, this kind of the elements are subjected to the simultaneous torsion. We have studied the concept of torsion and concept of bending, torsion and bending. When there is a simultaneous occurrence of torsional stress and bending stress, in this case, the maximum principal stress due to combination of these tensile or compressive stresses with the shear stress taken account. Keep in mind, maximum value of tensile stress, maximum value of compressive stress accompanied with shear stress. Then if this kind of situation arises, then we can use these formulas, that is the maximum tensile stress, maximum compressive stress and maximum shear stress, to determine the maximum values of stresses which are induced in that component when it is subjected to combined torsion as well as the bending. So these are the three formulas from which we can calculate the maximum tensile stress, maximum compressive stress and maximum shear stress. Next is the concept of factor of safety. What is meant by the factor of safety? Now when we are designing any element, and as we have studied, the criteria for designing any element is yield stress or ultimate stress. So by considering these two values, we have to consider a value so that the component do not break, do not fail when it is subjected to any particular application. Then we consider the factor of safety. In simple language, factor of safety is defined as the ratio of maximum stress to the working stress. Now when we have studied the stress strain diagram, at that point we have undergone what is meant by the maximum stress and what is meant by the working stress. It is also known as the design stress. When up to this stress, that is the working stress, that element is safe, that object is safe. And so by taking into account that value of working stress, we have to design that component. So factor of safety is the maximum stress. Again, try to understand, maximum stress is the value of stress which is induced in that component when the maximum load is applied on that element. That is the value of maximum stress, because we know that stress is calculated as the force acting on the element per cross-sectional area. So factor of safety in simple language is known as the maximum stress to the working stress, that is the design stress. This is the in general definition of the factor of safety. So we know that there are actually two materials are there from which we can manufacture different components, that is the ductile materials and brittle materials. Suppose if any element or any object is made up of ductile material or it is made up of a brittle material, and if we want to design that object, then we have to consider the value of factor of safety for ductile materials and different value of factor of safety for brittle materials. We have undergone the stress strain diagram. In case of ductile materials, say like mild steel, where the yield point is clearly defined. Means what? In case of ductile materials like mild steel, aluminium, copper, before actual breaking of the element, we can see a small amount of neck formation. That is the yielding. Means ductile materials do not break without giving any significant indication. Ductile materials give the indication that the ductile material will going to break if we going to apply the large amount of load on it. So that before breaking, the ductile material forms a neck formation, undergo a neck formation. That neck formation is nothing but the yielding. That point is the yield point of that material. So for this we have to consider the yield point stress as the design stress for that ductile materials. So this is our safe stress, that is the design stress. Then in this case, regarding the ductile material, the factor of safety is defined as, in general definition is maximum stress divided by design stress. Now in case of a ductile material, the maximum value of stress is the yield point stress, which is considered for the designing of any element. So in this case, we are considering the maximum stress as the yield point stress in case of the ductile materials. Take the example of in case of ductile materials, the factor of safety is defined as the yield point stress divided by working stress. Now take the example of brittle material. The example of best brittle material is take the example of chalk. If we apply a load on chalk, or if we bend a chalk, it will not show any sign of bending. It will just get break. Means there is no neck formation. It will not going to show any kind of indication that this material is going to break. So without any indication, it will get broken. So there is no case of yielding. Means brittle material do not undergo the process of yielding, the process of neck formation, and it will get broken. So that value is the ultimate stress in case of brittle materials. That is the value of stress where that material is going to break. That is the breaking stress. That is the ultimate stress. So this is the maximum stress in case of the brittle materials. That is the ultimate stress and working stress as it is. So in case of brittle materials, the factor of safety is defined as the ultimate stress. That is the maximum stress in case of brittle material is the ultimate stress to the working stress or design stress. So this is regarding the factor of safety. In general, factor of safety is defined as the maximum stress to the working stress. In case of ductile materials, the maximum stress value is the yield point stress, that is sigma yt. You can have a notation like sigma yt to the working stress. In case of brittle materials, the factor of safety is the ultimate stress to the working stress. Now, how to consider this factor of safety? Means, what are the criteria? Which value we have to consider for the factor of safety, and why there is a need to consider the factor of safety. Now, selection of factor of safety depends upon some certain parameters. Means there are certain parameters that need to be considered before selecting a particular factor of safety for designing a particular element. Now these parameters or these considerations which are considered for the selection of factor of safety are: the first consideration is the reliability of the properties of the material. Means what? Suppose you have considered a single element. Take the example of a mild steel. If you have considered mild steel, if that material is made up of a mild steel, and if we want to design that material, say a crankshaft, if I want to design that material, say a knuckle joint or a quarter joint or a lever, if I want to design that material, if that material is made up of a mild steel, say 40C8 or 30C8 or 25C8, then how reliable the properties of that material are, that we need to take into account, and change of these properties during the service, during the application. Whether that material is going to change its properties when it is subjected to the application due to the change in temperature, due to the change in load, due to the change in environmental conditions. If these kind of the considerations are there, if these kind of the factors are there, then by considering these kind of the factors, we have to decide or we have to select a particular factor of safety for that material. Okay, that is the reliability of the properties of the material and change of these properties during its service. This is the parameter on which the factor of safety depends. The second parameter is the reliability of the test result, the accuracy of application of these results. Means what? Suppose I want to use a certain part for manufacturing of the machine, and we have undergone some testing of that component. We have tested that component for tensile loading, We have tested that component for the compressive loading. We have tested that component for the hardness. We have tested that component for the toughness, and we got some results. And by looking at these results, or by considering that results are very good, we are using that component in the actual machine part. But if that results reliability, if that results are not reliable, means if that results are not accurate, then we have to go on the safer side. Means if that result is saying that its breaking stress value or its yield point stress is 380 Newton per mm square, if that results are not accurate, and suppose its yielding stress will be 300 Newton per mm square, now in this case we have to go on the higher side, because whether that results are accurate or whether that results are reliable, we don't know. That's why, by considering the reliability of the test results and the accuracy of the test results, we have to select a factor of safety. Third part is the reliability of the applied load. We have already studied the different types of the load which are acting on the element when that element is subjected to the particular application, when that element is subjected to the any load, that is whether it is a dead load, or whether it is a live load, or whether it is an impact load. So whether that load is reliable, whether it is acting, a constant load is acting, whether it is a shock load or impact load, we need to consider these considerations by taking into account the nature of the load, whether it is a tensile load or it is a compressive load. By taking into account the nature of load and the reliability of that applied load, we have to select a particular factor of safety. Fourth parameter is the certainty as to exact mode of failure. Means what? When we are designing any component, we need to understand the exact mode of failure, whether that component is going to fail due to the tensile loading, or whether that component is going to fail due to compressive loading, or whether that component is going to fail due to shear stress or bending stress. That exact mode of failure should be known to us, and we should have a certain about this, that what is the exact mode of failure of that component. If we are certain about that, that is the exact mode of failure of that component, then we can consider a factor of safety for that kind of a failure. Next is the extent of simplifying assumptions. Means before actually designing any component or any element, we are assuming some assumptions, we are assuming some criteria, that the material is do not losing its property when it is subjected to the application. There should not be any catastrophic failure. We are considering that no bending load is acting on that element. We are considering that its grain structure is very good. But in actual practice, this is not the case. If that simplified assumptions are not accurate according to the loading conditions, then we have to go on the higher side for selecting the factor of safety. The sixth parameter is the extent of localized stresses. Localized stress means stress concentration. Means at a particular point, what is the intensity of that stress which is going to induce at that particular point when any component is subjected to the application. What is the extent, what is the intensity of the localized stresses? That means a stress concentration will occur in that element. And if stress concentration will occur in that element at a particular point, then that element will fail before actually reaching the breaking stress of that element. And if that is the case, if there is a possibility of the stress concentration at a particular point, Then as a design engineer, we have to select the higher value of the factor of safety. Next parameter is the extent of the initial stresses set up during the manufacturing. So we are designing the component, means we are actually determining the dimensions of the component. And when we are going to deciding the dimensions of the component, we are considering the different stress values, different kind of the stresses which are induced in the component. If the initial stresses are set up in that component during the process of manufacturing, say the thermal stresses, if there is any kind of the pitfalls in the element, any manufacturing defects are there in the element, then these stresses also play an important role in deciding the breaking stress of that component. So before actually deciding the nature of the failure of the stress, nature of the failure of the component, due to which stress that component is going to fail, we also need to consider the nature of stresses which are actually set up during the process of manufacturing. By considering this fact, we have to go on the selection of the factor of safety. Next is the extent of loss of life in failure occurs. That is the most important point, because actually workers are working beside that machine, actually a worker is operating on that machine, and if any part or any service fails, then what is the loss of life in that case? Take the example of the aeroplane. Take this case of any simple element of the aeroplane. If you are designing that simple element of an aeroplane, we know that the number of passengers are traveling by aeroplane, thousands of passengers are traveling by the aeroplane. And if we have not considered the higher value of the factor of safety while designing any smallest element of the aeroplane, if that elements fail due to a particular stress value, then think about the loss of life. Major loss of life will take place in that case. That's why, by considering the intensity of this loss of life, we need to consider the higher value of the factor of safety. Means by taking into consideration this fact also, we have to consider the higher value of the factor of safety. Last is the loss of property. Same case. If due to the failure of any element in aeroplane, or say locomotive, or say marine ships, or say automobile, if that part fails before actually maximum stress value, then there will be a loss of that property. That loss will not be incurred. So by considering the impact of that loss of property due to the failure of any smallest element of the machine, or say vehicle, say automobile, or say any device, what will be the loss of the property and the loss of life? That consideration need to be considered while designing a particular component. So these are the 9 parameters that we need to consider while selecting a factor of safety. That is reliability of the properties, that is reliability of the test results and accuracy, reliability of the applied load, certainty of the mode of failure, simplifying assumptions, localized stresses, that is the stress concentration, initial stresses set up during the manufacturing, what will the extent of loss of life, and the loss of property. So in this lecture we have studied what is meant by the principal stresses, what is meant by the principal planes, what is the concept of the factor of safety, and how to consider the value of factor of safety by considering, or what are the considerations before selecting the value of factor of safety for designing a particular element. I hope you would understood this concept. Once again, thank you.